Welcome back. We're up to now part 4 of our lecture about wind turbines. And what I want to do in part 4 is kind of use HOTS, our horizontal axis wind turbines, with an upwind facing mechanism to be kind of our model of how we're going to talk about the basic structure of a system. I mean, really, whether we're talking about vertical axis or horizontal axis, whether we're talking about upwind facing or downwind facing, they're all going to need analogous parts. Well, maybe not VOTs, but we'll see. So what I want to do is I want to take some time to look more closely at what's actually going on with all the mechanics up at the top of that tower on like a VOT or whatever. Now, one term that we have used a lot of times in the course of this semester is the rotor. The rotor is both the hub, the kind of nose of the turbine, and its blades. The whole mechanism that is doing the rotating is called the rotor. It is made up of discrete blades and a hub, and they have very different roles, of course. More importantly, the blades need to be able to pivot inside of the on the surface of the hub to control the pitch of the blades. The pitch is, are the blades facing like this, or are they facing like this, or someplace in between? There's a pivot to each of the blades. And the pitch of the blades is controlled by the rather uncreatively named pitch control system that is actually inside the hub itself. Now, that might not seem like an amazing thing, but actually that is genius. And it takes enormous amounts of engineering to get this to work. Why do we need to adjust the pitch of the blades? Adjusting the pitch of the blades controls how fast the whole rotor is going to turn at a given wind speed. Now, we principally do this because there's going to be times where the wind speed is too fast, where you are exceeding the design parameters of the turbine to allow the wind to turn the blades to turn the whole rotor as fast as it can. You'll be exceeding the ability of the works that are inside of the rest of the turbine here to produce electricity safely and without diminishing the lifespan of the system and so on. So after you get faster than a fairly brisk wind, I mean the exact speed depends on the exact model and the radius of the blades and all that kind of stuff, the pitch of the blades will start to change based on the pitch control system that we'll be using to kind of start reducing the pitch or changing the pitch. That might be a better word. Actually, let's use the right vocabulary word. To feather the pitch. Feather. F-E-A-T-H-E-R. To feather the pitch of the blades so that even though the speed of the wind is increasing, the speed of the turbine is not increasing. And in fact, if the wind speed gets too high, we can actually completely feather the blades so that they're not turning at all. Similarly, there's no particular reason to let the turbine run at low wind speeds. Below a certain wind speed, the actual kinetic energy, remember the kinetic energy is, the flux of kinetic energy is proportional to the cube of the wind speed. So at very low wind speeds, there's not much kinetic energy to be captured. There's no point in doing the wear and tear on your system to capture such a small amount of electricity. So again, they feather the blades so that they're not rotating at all. And certainly as you go down the highway or something like that, you often see wind turbines that aren't turning. It's because based on the meteorological control systems that are on board the system, they have decided to completely adjust the pitch of the blades so that they are not rotating at all. Actually getting this thing to work inside the hub of the rotating hub of the rotor is actually an astonishing engineering challenge. The whole mechanism with the motors that are turning, well, sometimes it's electrical motors that control and hold the pitch of the blades. In some examples, it's actually it's a hydraulic pump that is controlling the pitch and holding the pitch of the blades. But no matter what, doing that inside of something that is spinning is a major engineering task. Okay, I mean, how do you even get electricity to the electrical motors or whatever there as the thing is turning? I mean, you have to have these what's the right word, slip discs and things like that that can transfer power as the motor is actually turning inside of the hub. It's actually an amazing bit of engineering to make that thing work. Alright, let's talk about some more parts here. Again, I just highlighted hub just to keep us going here. As we've used the word 100 times already in this class, the actual superstructure of, that is lifting the hub to the hub height of the turbine is called the tower. And the rest of the works of the wind turbine is inside of a small room kind of structure called the nacelle. Nacelle is a weird word. nacelle, don't even like worry about like other uses. You might know the word nacelle from other applications, like aircraft have nacelles, and like spaceships on Star Trek have nacelles and so on. Those uses of the word are related, but let's just focus on just calling that structure that's at the top of the tower the nacelle. Now, in the course of my reading about all of this stuff, I came across a number of different diagrams that show you what's going on inside of the nacelle that illustrate different features of what's going on in a wind turbine. Well, they illustrate some features better than others. And so let's just start with this one right here. If we were looking inside of the wind turbine here, and you can see there's a guy in there just sort of to give you a sense of scale, one feature that I want you to notice right away is the yaw mechanism. Can you see how there is sort of like gears around the edge of the tower there? That is showing where like there is a motor that can be used to drive the nacelle to turn, to pivot, nope, let's use the right word, to yaw around the edge of that tower to keep the rotor facing upwind. And the way that it does that is by it has weather instruments up on top of the nacelle, mainly anemometers and wind vanes, of course, that tell it and use its computers and so on to control the yaw mechanism to keep the nacelle facing upwind. Now, the turbine the rotor is going to be attached to a drive shaft. And the right term actually here, well, eventually that drive shaft is going to lead to a generator where the electricity is actually being produced. But we need a better diagram if we're going to be looking at that better. So I like this one from the Department of Energy's website. Coming off of that rotor, there is a shaft. And that first shaft is called the low-speed shaft. That is the shaft that is rotating with the same angular velocity as the the rotor itself is. Typically something like 30 to 60 RPMs, or revolutions per minute. In other words, somewhere between 1 and 2 hertz. No, I'm sorry, between a half and 1 hertz. Sorry. That's not very fast, okay? That will not be very easy to convert into electricity. That isn't really the way generators work. So what we need is a gearbox, where a system of gears will convert that, gears with different numbers of teeth and different radii, that are converting that low-speed shaft to result in a much higher speed that will be the shaft that rotates in and is captured, that kinetic energy is captured by the generator. Now, the gearbox then is kind of central to how this whole thing is going to work. And it turns out to be where a lot of the cost and a lot of the weight and a lot of the wear and tear on a wind turbine is. This thing is rotating. Anytime the turbine is going, it's going to be rotating, especially on its high-speed end, much, much faster than the turbine itself is. It's got to be up there running by itself. There's nobody in general up there, lubricating it and so on. This is a expensive, complex, heavy. This is a difficult part of the whole mechanism of a HOT. But the result after we get through the gearbox is, whereas the low-speed shaft entering the gearbox might have been rotating at about 30 to 60 RPMs, typically the high-speed shaft exiting the gearbox will be rotating at about 1,000 to 1,800 RPMs. That is a speed at which we can connect it to a generator to produce electricity. The generator is actually up there in the nacelle itself. That's something a lot of folks don't know. They assume that somehow or other, like, there might be a rotating shaft that goes down the tower of the windmill, of the wind turbine, and then like at the surface, that's where we have the generator. No, the electricity is actually generated up there in the nacelle itself by a generator. A generator, in general, is a piece of technology that can take any kind of mechanical energy that is rotating and convert it into electricity. And you have a little cheesy animation of that here from How Stuff Works. There's lots of different ways to configure a generator, but generally speaking, if you either are rotating a loop of wire with magnets on either side of it, or you have loops of wire where you're rotating the magnet around the loops, either way, you're taking rotational energy mechanical energy of rotation and converting it into electrical current, which then can go off to batteries or can go off to do work or whatever. We use generators all over the place in our day-to-day lives. I mean, that's how a coal-fired power plant works. That's how a nuclear power plant works. That's how hydroelectric power plants work. They all are about taking rotational energy and converting it into electrical energy through induction in a generator. Now, the electricity that's being produced by the generator needs then to come down the tower, which I've illustrated there with that wire there. There's also other cabling that needs to come down the tower. Cables that can, are getting data from the sensors and measurements from, the gearbox and things like that. And I don't want you to get the idea that these are like, just wires. Think more like a garden hose. Okay, they are thick cables with big, thick, insulation around the outside there, and they have to work their way down. This is a big problem because if the nacelle is going to be yawing in the same direction, multiple rotations, that cable is going to get all twisted. Now, I kind of comically drew it as it's wrapping around the outside of the tower here, but that isn't what's going to happen. But inside it's not that far off. I mean, those cables that are running up the tower, they're generally attached to the inside of the tower so that there's also a ladder that the crew can go up and down. So they are attached to the inside of the tower, and then at some point they are not attached anymore. There's some slack, there's some excess cabling, and then they go up to like the generator. Well, as the generator turns, therefore, it's getting knots in that it's twisting the cabling. That could be a real problem. Well, it's an engineering problem. You throw engineers at problems, they'll make a device that can deal with it. In this case, they have invented a piece of equipment called the cable twist counter, and it's not particularly relevant to actually show you a picture of it. It's just a little box. But it actually can measure how many twists there are. Now, what are you going to do about that? Well, if it's it's active yaw control, where there's actually motors controlling the yaw, what you can do is stop the windmill by adjusting the pitch in the turbine, by adjusting the pitch of the blades, and then literally powering the turbine through some rotations to make it untangle. So drive it the opposite direction a few times. I really looked all over the place on YouTube to find some examples of this because several websites said, go look for them. They're great to watch these turbines turn on their own to go, and untangle their cables. And the problem is that a lot of these kind of videos are not in English, and I just couldn't make any sense as to what I was seeing on some of them in terms of was that actually an example of untwisting the cables and so on. But I can picture what's going on. If I have active wind power, active yaw control. If I have passive, I've got a bigger problem, okay? Now it's going to require a crew to come in here and actually detach the cables, untangle them, and put them back up. Does it happen? Well, yes. In general, does it happen? That's a harder question. I mean, do we in general expect the wind to yaw through 360 degrees and then yaw through 360 degrees the same way and get the cables all tangled up? In certain regimes, that's going to be more common than others, in certain locations and so on. But that's something you're going to have to know before you decide if you're going to put a wind farm or whatever in a particular location and how you're going to address that problem. Now, one way around it is to just not use cables to transfer the power down to the ground. Use cabling to connect the power to, it's called a slip ring, where the two metallic rings are touching each other, and as they go, as the cell turns, the rings stay in contact with each other, and the electricity being produced by the generator will just flow through those rings and then to cables that take it down to the power. So you're, using this sort of slip ring technology. In general, that's not a great choice if we're talking a very large turbine. That kind of slip ring technology is not going to work if we're talking much current. A small demonstration wind turbine at like a school or something, that would be fine. But for something commercial, that kind of slip ring technology is not going to be the tool for the job. Alright, let's answer a couple quick questions before we go on to a fifth and final part of the considerations associated with designing a wind turbine. Question 10. Why is there a gearbox attached to the shaft that is directly turned by the rotor? A, it can stop the rotor from turning in the event of a catastrophic mechanical failure. B, to increase the rate of the shaft, the rate of the shaft's rotation so that it can efficiently produce electricity in the generator. Or C, it keeps the rotor facing perpendicular to the wind. Oh, which of those are why we have to have a gearbox in the nacelle of a horizontal axis wind turbine? All right, make a choice from those three options and get a little feedback before we go on.